Hello, my name is Joel Chatfield, and this is my presentation for Lab 2. Um, Introduction. The goals are to find the distance dependence of a magnetic field of a small bar magnet. We're then going to simulate that field in an online Python code set, and then compare the measured versus simulated fields. So this is just my standard measurements I took. The magnetic dipoles are roughly 1.4873 amps per meter squared. The uh, off-axis field when measured was 6.71958 microteslas, or e to the negative 0.5 teslas, and it was 2.945 e to the negative 5 teslas for the simulated one, so it was much smaller. Just the equations and concepts. That top one is just going to be our bar, the approximation we're going to use for on-axis. Below it is how you're going to turn into a linear graph, and then that last one is the actual equation that we'll use later on for simulated. This is just a standard representation of what the visualization of a bar magnetic field looks like. You'll see it's pointing left towards the North Pole. The experiment, so I located the magnetometer on my phone. You then turned and adjusted it such that it was pointing roughly towards magnetic north, so it was fluctuating near zero. He then took measurements at 20 microtesla, 70, 120, 170, and 220. He just moved the magnet till it got about there and then measured the distance, took 3 measurements of each, and then did the same thing with the magnet at a 45-degree angle from the phone, specifically at 100 microteslas. So this is all the data I pulled. You can see the averages over there on the left. You can see the graph is decreasing, showing a relationship such that the further away it is, the smaller the field is, and then down at the bottom is the off-axis field measurements. So observations. When the magnetometer is far away from the magnet, it measures a near zero magnetic field in the x direction. As r goes towards infinity, gets very, very far away, the actual equation goes towards zero. And then as it moves closer, r gets smaller, so the x component gets bigger. And then on the right is the equation I used to solve for the magnetic dipole moment once I found K. So this is just the code. This is all the constants and how I found the dipole with the equation at the bottom. It's the code for creating all the arrows and positioning them so they would show up on the code. This is the code for the off-axis measurements. And then you can see all the arrows. The yellow arrows are the on-axis that's pointing right, or the yellow arrows pointing right are the actual on-axis, and then there's the perpendicular axis, which is the blue arrows. The reason that one in the middle is big is because I couldn't figure out how to turn it, so it's actually 2 arrows pointing left overlaid, which is why when 2 of them add together, they're the same as the parallel ones, and then that pink one in the top right is the 45-degree angle one. As you see, it's much smaller because it's further away from the others than the others are. So things I discovered. Magnetic field strength and distance have an inverse relationship, so the farther apart they are, the smaller the field is. There's a large disparity between the observed and simulated fields. Possible sources of that error could have been nearby electronics generating a field, meshing up the measurements, inconsistent phone placement such that the magnetic field to the Earth might not have been exactly zero. Error in measuring the distance, if the magnet got shifted whenever I was measuring distance, or I didn't have it perfectly aligned with the magnetometer, and imprecise placement of the magnetometer. You kind of just found like a range, and it wasn't perfect. So what if? What if in the experiment you oriented your set? You didn't do that. You didn't set it up to be towards magnetic north. You would have had a different x, either larger or greater, depending on how your phone was oriented. But the field of the Earth would have affected your measurements. And second one, what if you stuck two identical magnets together? You would have just had an approximately double measurement of the field because you could have treated it as simply one larger dipole with double the charge. So it would have just measured double.